let's have a look at the following theorem, another form of fundamental theorem. Okay, so it says that if we have a continuous function f c0 on the closed interval EB, we can define the function and g of x defined by like an area from a to x of ft dt. Okay, for x, so we can define it for x between x belonging to from a to b. Then the conclusion is that g is differentiable. Okay, g is differentiable function, differentiable on the closed open interval EB, and we have g prime at x equal fx for any x, for x, okay, for x belonging to the interval EB, open interval. So this is what the theorem says. So we can, knowing given a function, continuous function, we can build an antiderivative. We know it is given as a definite integral from e to x for each x. Okay, so now you see how important, so how we can define antiderivatives. Okay, so we have some remark as just notation here. So g prime, so that is we can write dx of e to x ft dt equal f at x. Okay, f takes the value at x at point x. Okay, so we will not focus on the proof of this theorem. Let's do some applications here. Look at some applications. So what here it is. Here is g of x defined by the definite integral from 0 to x of square root of 1 plus t square dt. Okay, and the question is to find the derivative. Okay, so yes, the derivative then, so we don't know an antiderivative of square root of 1 plus t square. Now the fundamental, let's see if we have the conditions are satisfied. So here for our situation, we will have ft is square root of 1 plus t square. F is, so it's, yes, it's continuous everywhere. Okay, so we have the conditions is satisfied, therefore g is differentiable, and the derivative is nothing that fx, f at x, that is square root of 1 plus x2. Okay, so now let's what if I'm given the function h of x equals square root from 0 to sine x square root of 1 plus t square, and the same question is given. So this time where the question is to find h prime of x. Okay, so this time you see you have here the endpoint is sine x, it's not x, so I'm not under the same assumptions of the theorem to apply it, but let's try to bring ourselves to the same conditions. So let's introduce the function fx, so capital Fx, as from 0 to x square root of 1 plus t square. So this one is exactly as it, I know that its derivative is square root of 1 plus x2, or why changing the name, it's our g, the previous g. Let's keep the same notations. So we have g of x, yes, and this is g prime then. So we already did that, so let's just erase this line. We don't need it. Okay, we already yes. Then I can express h as h. I can write it as g at sine x. Okay, so it is a composition function. Therefore, g as sine x, a sine function is differentiable everywhere. G here is differentiable everywhere. So yes, IH is also differentiable, and the derivative is g prime at sine x times the derivative of sine, which is cosine x. Now g prime, we computed it, its square root. Yes, so it will be the square root 1 plus apply that sine x, so it will be sine x square. Okay, everything times cosine x. So here is how you can apply this fundamental theorem. Now a second theorem that is called the important theorem, called the mean value theorem for integrals. So let's write it here. Mean value theorem for integrals. So the theorems where the assumptions are continuity of f, c0 on EB, and then the enough, that's all. Then there exists c inside. It can be, yes, so it can take e or b as value, so it belongs to the closed interval, such that you have fc is 1 over minus e of ft dt. So this quantity is called average of a function. So we will explain later why is it f average. Okay. So I would like to give you a hint of the proof because it's very simple and very, you will see it uses the previous theorems you know. Let's give it quickly. So using the fact that f is continuous on the closed interval EB, then by the extreme value theorem, so by the extreme value theorem, we know that there exists x small m inside EB, also x capital M, such that my function f attains its minimum value at xm, okay, and it attains at x capital M its maximum value. Okay, so my function is always between those two values. Let's put small m and this quantity capital M. So it's between m and capital M. Okay, now let's okay, so now let's integrate, because we want this quantity in the integral. So if you integrate, we use inequality. So you look here, we use the mean extreme value. Here we use by comparison. We use the comparison between functions and areas. So we will obtain that m times b minus a is less than a to b of fx dx less than m b minus a. Then divide by 1 b minus a. So we will have this quantity. We can change the variable if you want, ft dt, between capital M and small m. Okay, and this is exactly f at, we said at xm, and this is exactly f value taken. Okay, so now, so this is, if you remember, if I call it k is between two values of the image, of f. Then by the intermediate value theorem, we know that there exists c inside EB such that fc equal k. And this is how we establish the proof of theorem. So it uses three results that we already know. Okay, now why is we call it an average? So we can, yes, so there is an explanation for that. So we can, for example, so let's give it as a remark, maybe. So as a remark here, okay, a remark. So the concept of average, so you take values over n and gives the average. Okay, okay is the average of the function, average of n values. Okay, this is y average. Okay, so suppose that we have divided our interval AB in subdivision, and the y1 are assigned, are taken, are, yes, are fx1 star plus fx n star over n. Okay, now we know that we use delta x as b minus a over n, so then n can be expressed as then n. Okay, then n you can write it as b minus a over delta x. Okay, so this quantity, this sum of fxi star, you will have then b minus a and over delta x multiplied delta x here. Okay, equal y average. And if you increase the number taking n to infinity, then you will get yes, the average, the meaning of average. Okay, if the limit exists, so this is exactly will be the integral, and this is y average. Okay, this is why we call it average. Okay, now there is a geometric interpretation of this theorem. Geometric interpretation. So we can read it first, the equality, we can write it differently. We are saying that the integral from e to b of t dt is equal to b minus a times fc. That means if you graph your function, here is e and b, here is the length b minus a, the side b minus a, okay, distance. FC, there is some c somewhere, okay, FC, and this is an area of a rectangle, area of a rectangle. So we can graph our rectangle, and it says that this area is equal to the area under the total area under the curve. Okay, so here imagine my curve goes somewhere, does something like that. So this quantity in green measures the area, gives exactly the area. Okay, so I said FC, here is FC. Okay, here is my FC. So this is what it means. For the first theorem, we will see its application later more. Why is it so important? We will see it. It's not just for derivative, but it's more. Okay, so this is about a fundamental theorem and mean value theorem. So, and fundamental theorem and the mean value theorem for integrals. Okay, so this is what we saw today.